Hello, welcome to our senior design presentation. My name is Jaqueline Barbosa, and I'm a visitor student from Brazil.
And my name is Kirsten Petersen, and today we're going to share with you our project called Energy Made in Uganda, a locally manufacturable and serviceable solar home system. So let's take you to Uganda. In the rural areas of Uganda, there is only a 3% electrification rate. With this lack of electricity, people turn then to inefficient fuel sources such as kerosene, as shown here in this lantern. These fuel sources pose very negative effects on the health, safety, and the environment in Uganda. However, there is a very hopeful opportunity, and it's going to be demonstrated over here in this solar insolation map. Solar insolation is the amount of the sun's energy which reaches the Earth's surface in a given region. As you can see from this, there is a lot in Uganda. For this reason, solar photovoltaic energy is a very viable alternative to these inefficient fuel sources.
So as we could see, there's a lot of room for growth in solar in the Uganda market. So let's see how solar looks nowadays. In this table shows some products international manufactured for houses and small business, and the costs vary from $50 to $500. Unfortunately, when those products malfunction, there's no local expertise to service them. The products remain broken, people lose trust in solar, and this leads to market spoilage.
To combat this issue of market spoilage, 4 graduate students of a solar certificate course in Uganda have started a community-based organization that they call Energy Made in Uganda. What this group is doing is trying to make solar a sustainable energy source within their own communities. And they're doing this by increasing the local technical capacity or through the manufacturing, servicing, and sales of solar home systems. The system that they hope to sell is locally manufacturable, which means you might only be limited to using a soldering iron and not much more. It has to be price comparable to the internationally manufactured products that we've just seen, and has to meet the local need. And who better to know that need than the community members themselves? Additionally, because energy needs differ so much between businesses and single homes, this system needs to be modular to scale with battery size and panel size. So for our senior design project, Jackie and I are collaborating with Energy Made in Uganda to design the electronics of this system.
The electronics we're designing go inside this black box, and the first idea of the students was to hit a rural area, Uganda, providing them a basic solar home system, which would include the solar panel, the box with electronics, and the battery. So our project is all about DC to DC power conversion. So we need to step down the output voltage from the panel to provide the right amount of current for the battery, and regulating a constant voltage on that load. So there are 2 ways to do this. We can use linear regulators or switching regulators. Linear regulators dissipate a lot of power because they act as variable resistor. And switching regulator has the advantage of being more efficient. So let's see what's inside this box. Here is our system block diagram. As you can see, we have the PV panel, the charge controller, a power path control, the battery, and the DC to DC step-down converters. So let's explore a little bit the PV panel. We are using a 10-watt panel by Solar Sunshine, and we chose this panel because our customer needed something cheap, and it was just $12. We modeled this panel using LT Spice, a software to simulate circuits, and we got the IV curve. The IV curve is the behavior of the panel. So here we can see the open circuit voltage of 21.6 volts, and there the short circuit current of 0.68 amps. So this is the behavior of the panel, and the load line is the behavior of the system. The intersection with those two graphics give us the maximum power point. At this point, the panel will provide our optimal charging for our battery.
So what battery are we using? This right here is the system battery. We are using a 6-volt, 4-amp-hour sealed lead-acid battery. What's interesting about this is 6 volts is generally not an industry standard, but our reasons for choosing this battery are rooted in the fact that it is the most prevalent battery in Uganda. The reason being is that it's the battery that's used in the motorcycle taxis. And motorcycle taxis are an extremely popular form of transportation, so this high demand drives the prices down. So we're able to get this battery for the US equivalent of only $4. Knowing that the chemistry of this battery is sealed lead acid, we have to take into account that it has a very characteristic charging cycle. It's divided into 3 stages. The first stage is charging, and at that point, this blue line represents the current, so we want to hold a very high current on this as the battery voltage increases to its full charge state. Once the voltage is reached, the current will drop off until it reaches the standby mode, and at that point we're going to have a very, very small trickle current, and that's just to keep the battery from discharging. So the next component of this system that we're going to describe is what is called power path control. This is also often referred to as day-night switching. The idea behind it is we have 2 energy sources in our system, so we want to control at what time each of these is being used to power our loads. So during the day, when the sun's shining on the panel, that's going to have the highest voltage in our system at 18 volts. So this day diode is going to turn on, and it's going to bring the power to the loads. However, once it becomes nighttime and there's no longer any solar energy on the panel, the battery becomes the highest voltage in the circuit, in the system, and it's going to be the one directly powering our loads.
So why do we need a charge controller? The charge controller is important because it's going to meet the charging requirements for our battery. So our battery has some charging stages, so we need to meet those. The charge controller also avoids overcharging and deep discharging. The previous design, they used a normal DC to DC switch regulator, and they couldn't get the 1.2 amp for the battery. So our first solution was to analyze if a Darlington pair, use a Darlington pair to boost this current, and we also need a current limiting to behave as a charge controller. But after this analysis, we realized that this was way too expensive and complex, and we decided a more simplified solution.
So our solution is in the form of an integrated circuit battery charge controller. There are a number of these chips on the market, and they offer a simplified solution all in a single package. So we looked mostly at products by Texas Instruments and Linear Technology because they do offer so many battery power solutions. They all perform the necessary characteristics to serve as our charge controller, and because of that, one of the things that made us make our decision was the price. As you can see, the LT3652 HV by Linear Technology is priced at $3.70, so it was our clear option. The package that this chip is called a DFN12, and another thing that we found very appealing about this is despite it being surface mount, this chip package is able to be hand soldered, so it can be manufactured in country. Additionally, at no extra cost, this chip provided us the option for taking advantage of maximum power point tracking, as Jackie was talking about.
So after analyzing and choosing the chip, we started our simulation using LT Spice. So this is the model of the LT3652 HV. And here are the desired features we want to our system. We can see here the day-night switching is performed by the two Schottky diodes. The charge indicators, the charge pin and the fault pin is to the battery stage. So when the battery is charging, we are going to see the light, the green light, and the fault is for bad battery conditions. We have here the RSense. This is the inductor resistor for sensing the output, the maximum output current. So we set this sense next to the switch pin. This pin is important because of the main characteristic of the switching regulators, that the switching cycles. The feedback voltage divider is to set the output current. Once we choose our output current, our battery, so we put in this formula the float battery, and we pick the first feedback resistor. And then with this value, we have the second one. So we can scale up 6 volts or 12 volts. Here is the voltage in the switching pin. As you can see, the 6 volts and the 12 volts, there is a duty cycle. That's the relation between the output voltage and the input voltage. So
then we know we want to get that 1.2 amps out of this charge controller when our battery needs to be charged. In order to do that, we program the inductor resistor, sense resistor, which is also called RSense, using this relationship. This results in an extremely small resistance value, but because the currents that are going through this are so big, we had to use a very high wattage resistor. So the voltage across this RSense resistor is how we're going to program that output current. And you can see in the resulting waveforms, it has this characteristic triangular shape, and that's because it is the same current that's going through the inductor, and that's how it looks. So we have it both for the 6 volt and 12 volt system. In our LT Spice model, we also wanted to make sure that we were getting the right currents out as we were desiring. This red line is a model of the battery shown from a discharge state to charged. So as you can see, we got the 1.2 amps we wanted, and once that battery reaches its full voltage, 20 milliamps, a small trickle current is received.
So after we have all the simulations, we start to validating our design using the demo board 1568A from Linear Technology. Here we see the duty cycle, the voltage in the switching pin, and here the voltage in the RSense, as we analyzed it before.
And after confirming our design in LT Spice simulation, our next step was to actually build it on a breadboard. And we were able to do this using our surface mount chip by using a DFN12 to DIP12 adapter, and that's also referred to as surfboards. So one of the most important aspects of power electronic design is designing the printed circuit board. And it's also been proven to be one of the more challenging aspects. This image here shows our first layout, and the main things we were taking into account at this point was to keep the traces as short as possible because we want to decrease the inductance. So on printed circuit boards, noise is bad. So in order to decrease this, because we have such large changes in current on this, we want to make sure that this inductance value is as low as possible. So on that previous design, we had the entire backplate grounded. We soon learned that this was not a good strategy because it introduces so many vias, and every via acts as an inductor. And as one of our industry mentors likes to say, every printed circuit board is just one via away from destruction. So to solve that problem, what we've instead done is put just this single ground plate, which is under all of our noisy components. So divided almost exactly down the middle, we have our switching components on the top and the non-switching on the bottom. so that this is our noisy ground, and then the smaller ground traces serve as a signal ground. So the next part of our system, which we had to design, is the step-down converters, which go from the panel and battery voltage to our desired loads. Originally, the original system that Jackie mentioned, where it used only a step-down converter as the charge controller, used this chip. And while it wasn't appropriate as a charge controller, it is extremely applicable as for our step-down to the loads. This chip is the MC34063, which is a Texas Instruments part, and it is extremely inexpensive, which is appealing. Also is through-hole, so it's very easy to solder. And one of the most important things is it is able to handle that wide input range, since we have to vary between the panel voltage and the battery voltage.
So this table shows our cost breakdown, and it's now $30.15. We want to make sure to get a product cost competitive with those international manufacturer ones, and also with the previous design from Energy Made in Uganda. So the first design was $60 with labor, so we are on the track of this price. The next steps for our project will be to test our system in all loads and external conditions, and send the students in Uganda some boards and components for them to test and assemble together with us. And then we are going to include a manufacturing plan, and we are going to teach them how to surface mount soldering technique. And this project will continue to be scaled up to 12 volts to a 12 volt system because of the demand of the customer. And we are going to create. They are going to create a housing for the electronics. So our lessons learned. We learned a lot through this project. We learned engineering technical and non-technical lessons. So we could apply our engineering knowledge for creating, developing a product with a lot of contact with a customer, and also in a tight economic constraint.
This project is very unique in that it did involve so many players in the product design process. We were working with professionals ranging from engineers in Silicon Valley to solar technicians in Mpigi, Uganda. So as a result, we learned so much about communicating across nations, across time zones, and a lot of this, a lot of the discussions that came up, it was very difficult to come to a conclusion. Mm-hmm. And oftentimes we even learned that the customer is not always right.
Yeah, we want to give them a sustainable solution. Our first feedback was to try to change their system from 6 volts to 12 volt system because the market is trending for it. But they want to continue to use the 6 volt battery because it was really cheap and available in country.
We also spent a lot of time presenting to our customers why we believed it was necessary to add this charge controller to their system, especially if they want it to be a sustainable system where the end user won't have that large cost burden of having to replace the battery unnecessarily. Additionally, another thing was with the surface mount versus through-hole. By Jackie and I learning the surface mount soldering technique and now being able to teach it to our contacts in Uganda, we are able to prove that this can still be locally manufactured.
So besides of all those challenges, we can say that we could provide our customer with an easily manufactured product, with sustainable design that meets the customer needs and cost competitive.
So we want to close on a picture of the Solar Technology Lab in Mpigi, Uganda. This is where Energy Made in Uganda sells and services solar home systems. It is our dream to see one of these in every rural community in Uganda, and Jackie and I are extremely proud to have been a part of making solar energy a sustainable energy option in Uganda.
Okay, just finish. We want to thank all those people for helping us.
Are there any questions?
Are there any questions?
Yes.
So you talked about scaling up the from 6 volts to 12 volts, but what about power scaling? What is the scaling then for pure output power of the system? Is that scaling as well? Are you cutting the current in half? Are you doubling the current? I mean, what's the requirement then for that type of, you know, overall scaling of the project?
For the system scaling, the feedback that we've been getting is that it's more of what the increasing energy demands are for applications, and the biggest one is televisions. Mm-hmm. I had the opportunity to go to Uganda this last summer and interview a lot of people, and that was the #1 response of what, if a system could provide electricity, what they'd want. So the 12 volts would then introduce the ability to have a television like one might have in an RV, those small 12-volt televisions. Additionally, with now how popular smartphones are getting, those tend to not be able to be handled on smaller systems. So that would be an addition, as well as laptop charging capabilities.
And this is also not part of our project. Our project is just to design the 6-volt one, and the next step will be to scale up.
So you have 6-volt batteries, and there was the decision about 12 volts, but 2 6 volts in series equals 12 volts.
Right.
Is that an option?
Yes, then you can go for that one.
Yeah, is that an option because it's the most cheap battery, but they have also a 12-volt battery that's the same price, so maybe it's
How about hardware reliability and repairability in the field? Have you determined what the most likely repair requirements are going to be, since they have to sustain it?
A lot of what they've told us from the Skype conversations we've been having is that it'll be the blocking diode on the panel will get blown, or a lot of it is actually more of environmental wear and tear, like dirt will get into the system and you'll have to be able to fix that, or a wire will become loose. So a lot of it would just be routine maintenance, but we have intentionally, the reason we're mostly looking at the Linear and Texas Instruments parts is because they do have that reputation for being reliable. And that was also why we were sure to have them, so that if it breaks, which we've experienced burning out the chips a few times, and they're very easy to solder off and solder back on to fix. So we were able to prove in our lab that it can be done with just a simple soldering iron.
yeah.
Do you want to add anything?
The IC that you guys chose, it has a big ground pad on the bottom, but you said it
Yes.
could be soldered by hand. I'm just curious as to, how did you get that ground pad soldered for that part?
We use this soft board,
Uh-huh.
and we had the ground solder in the back. Is that the question? But it's simple. It's very simple to do it.
And then to actually get it onto the board, what you do is first you make it involves the use of a handheld heat gun, and you make layer the plate with solder, heat it up, then you solder on the legs, and then that's it.
I understood that. I was asking about this stuff.
This is going to have to be one more question, so we're running out of time.
Yes.
So you mentioned the wide availability of the 6-volt battery in Uganda. What about the other materials on your BOM? Are they widely available? And if not, have you factored in transportation costs?
There's available the panel and the battery, and all the other components we are going to purchase by DigiKey or some websites like that.
And the resistors and capacitors are easily found in the capital of Kampala. But as for the other ones, they are imported, but that's what they're doing right now, so that price is factored in.
Great presentation.